Hey there. Ready to dive into something truly mind-blowing. Today we're tackling a groundbreaking achievement in quantum computing. Imagine a world where computers can perform calculations millions of times faster and solve problems that are impossible for our current technology. Well, buckle up because researchers at the University of Oxford just took a giant leap towards making that a reality.
What's so exciting is that they've managed to achieve single qubit gates with error rates below 1 part per million. That's like flipping a coin 7 million times and getting tails only once.
Okay, I'm intrigued but also a little lost. Can you break down what this 1 part per million thing actually means and why it matters so much?
Think of it like this. Errors are the enemy of quantum computing. Every time a qubit, the basic unit of information in a quantum computer, undergoes an operation, there's a chance for an error to sneak in. These errors can snowball and completely derail a calculation. It's like trying to bake a cake with an oven that is a wildly fluctuating temperature. You're not going to get the results you want.
So this breakthrough is all about getting those quantum ovens to hold a steady temperature.
Exactly. What the Oxford team has achieved is a level of precision that's never been seen before. Their single qubit gates, which are the fundamental building blocks of quantum computations, are remarkably accurate. This means fewer errors, more reliable calculations, and a huge step towards making quantum computers practical for real-world problems.
This all sounds incredible, but I have to admit I'm still wrapping my head around what these gates actually do.
Imagine them as the logic gates in our everyday computers, but with a quantum twist. They manipulate the state of a qubit, kind of like flipping a switch between a 0 and a 1. But in the quantum world, things get a lot weirder. These qubits can exist in a blurry state of both 0 and 1 at the same time, which is what gives quantum computers their incredible power.
Okay, so we've got these super delicate qubits that can be in multiple states at once, and we need these gates to control them with incredible precision. And this is where the Oxford team comes in with their groundbreaking achievement.
You got it. Their research, which was just published on December 6, 2024, details how they used a trapped ion system to achieve these record-low error rates. Now, this is where things get really interesting.
Hit me with it. What's so special about this trapped ion system?
They used a calcium ion trapped in a special electromagnetic field, and instead of using lasers, which is the typical way to control qubits, they used microwaves.
Microwaves, really? Isn't that like trying to thread a needle with a sledgehammer?
You think so, right? But they were able to focus those microwaves with incredible precision, allowing them to manipulate the calcium ion state with remarkable accuracy.
Okay, so they got this ion trapped and they're nudging it around with microwaves. But how did they manage to get those error rates so low? There must be tons of things that could mess things up in the quantum world.
You're absolutely right. Decoherence, which is basically the qubit losing its quantum information over time, is a major challenge. It's like trying to write a message on a beach on a windy day. The information quickly fades away. And then there's leakage where the qubit state drifts outside its intended space. But the Oxford team tackled these challenges head-on.
So how did they pull it off? Did they have to build some sort of super cooled, vacuum-sealed, shielded chamber to make this work?
Nope. Remarkably, they achieved all of this at room temperature and without any bulky magnetic shielding, which is pretty amazing when you consider they were working with microwaves. It really speaks to their ingenuity and the incredible progress that's been made in trapped ion quantum computing. But even with this incredible level of precision, there were still some tiny errors.
I'm dying to know what caused those errors and how did they measure them with such incredible accuracy?
It's a combination of factors, and understanding them is key to making quantum computers even better. For example, they found that even the tiniest fluctuations in the microwave signal's amplitude could throw things off. It's like trying to walk a tightrope in a hurricane. Even the smallest gust of wind can make you lose your balance. But here's the thing. They developed these incredible techniques to constantly monitor and adjust the microwaves, keeping everything perfectly in sync. It's like having a tiny quantum conductor leading an orchestra of ions, making sure every note is played flawlessly. And to measure those tiny errors, they used a clever technique that basically involved throwing millions of random operations at the ion and seeing how well it handled them.
Okay, that makes sense. So they've created this incredibly precise system, but as we discussed earlier, the real magic of quantum computing lies in getting these qubits to work together. That's where those two qubit gates come in, right?
Exactly. Think of two qubit gates like getting two of those delicate ions to do a perfectly synchronized dance. It's even harder to control than single qubit gates, and the error rates are still higher. But this research is a huge step in the right direction. If they can achieve this level of precision with single qubit gates, it opens up incredible possibilities for tackling those more complex two-qubit operations.
So this research is not just about building faster computers, it's about laying the foundation for something much bigger.
Precisely. The level of control they've achieved has implications far beyond just computation. We're talking about a whole new era of sensing and measurement. Imagine sensors that can detect the tiniest changes in magnetic fields, gravitational waves, or even individual molecules.
Okay, now we're talking science fiction level stuff. I can see how this could revolutionize fields like medicine materials, science, and even our understanding of the universe. But let's get back to the nitty-gritty for a moment. You mentioned that they were able to achieve all of this at room temperature and without any bulky magnetic shielding. Can you explain how that's even possible? I always thought quantum computers needed to be kept in these super controlled environments.
That was the common thinking for a long time, but this research really challenges those assumptions.
Yeah.
The team at Oxford used a microfabricated trap to hold the calcium ion. Think of it like a tiny electric prison designed to perfectly confine the ion. And they integrated a microwave resonator right onto the trap chip, which essentially focuses those microwaves right where they need to be. It's like having a tiny magnifying glass for those microwaves.
That's amazing. So they created this tiny self-contained system that can manipulate these delicate qubits with incredible precision. It really seems like they've thought of everything. What were some of the other challenges they had to overcome?
Well, as I mentioned, decoherence is a major foe in the quantum world. It's like trying to have a conversation in a noisy room. The information quickly gets lost. They were able to measure a decoherence time of about 70 seconds, which is impressive, but it means they have a limited window to perform their operations. It's like trying to solve a complex math problem before the timer runs out.
So they're not only working with these incredibly sensitive qubits, but they're also racing against the clock. That adds a whole new level of difficulty.
Absolutely. And then there's the challenge of leakage, which is basically when the qubit state drifts outside its intended space. They found that even the slightest fluctuations in the microwave signal's amplitude could cause errors. It's like trying to balance a spinning plate on a stick. The slightest tremor can send it crashing to the ground, but they were able to address these issues with remarkable ingenuity.
It sounds like they were constantly battling these quantum gremlins, always trying to keep everything perfectly in balance.
You could say that.
Yeah.
But it's their meticulous attention to detail and their deep understanding of the system that allowed them to achieve such groundbreaking results. They really pushed the boundaries of what's possible in quantum control.
This has been an incredible journey so far. We've gone from these mysterious qubits to these incredibly precise microwave-wielding traps. But I'm eager to explore the bigger picture. What does this breakthrough really mean for the future? What doors does it open?
That's a great question, and is one that researchers around the world are grappling with. This level of precision in quantum control opens up a whole new realm of possibilities. But before we dive into that, let's take a moment to appreciate the sheer ingenuity and perseverance of this team.
I completely agree. They've achieved something truly remarkable. But I'm ready to have my mind blown even further. What's next?
Well, if you thought the science we've discussed so far was incredible, just wait until you hear about the potential applications. We're not just talking faster computers, but a whole new way of understanding and interacting with the world around us. We're talking about unlocking a whole new level of understanding and control over the world around us.
All right, I'm all ears. What kind of world could this level of quantum control unlock?
Well, for starters, imagine a world where we can design new materials with unprecedented properties. Think super-efficient solar cells that can capture nearly all of the sun's energy, lightweight but incredibly strong materials for building spacecraft, or even room temperature superconductors that could revolutionize electronics and energy transmission.
Okay, that's pretty impressive. But how does this breakthrough in quantum computing actually help us achieve those things?
It all comes down to simulation. Quantum computers could allow us to simulate the behavior of matter at the atomic level with incredible precision. This means we could design new materials from the ground up, understanding exactly how their properties will emerge based on their atomic structure. It's like having a virtual laboratory where you can experiment with different combinations of atoms and see what happens.
So instead of spending years in a lab mixing chemicals and running experiments, we could use quantum computers to design and test new materials in a virtual world.
Exactly. And it's not just material science that could benefit. Think about the field of drug discovery. Imagine being able to simulate complex molecules and design drugs that target specific diseases with incredible accuracy. This could lead to new treatments for cancer, Alzheimer's, and countless other diseases that currently have no cure.
It's incredible to think that we could be on the verge of such a profound shift in medicine.
And let's not forget about artificial intelligence. Quantum machine learning algorithms have the potential to outperform classical algorithms in areas like pattern recognition, data analysis, and decision-making. This could lead to self-driving cars that are even safer and more efficient, personalized medicine that tailors treatments to your individual genetic makeup, and AI systems that can help us solve some of the world's most pressing problems.
Okay, my mind is officially blown. This isn't just about faster computers, it's about unlocking a whole new level of understanding and control over the world around us. But with such powerful technology comes great responsibility, right? What are some of the ethical considerations we need to think about as quantum computing continues to advance?
You bring up an important point. As with any powerful technology, there's always the potential for misuse. Quantum computers could be used to break encryption algorithms that protect our financial transactions, personal data, and national security. It's crucial that we develop safeguards to prevent these technologies from falling into the wrong hands.
So it's a race against time. We need to develop the ethical frameworks and safeguards before the technology outpaces our ability to control it.
Exactly. And it's not just about preventing misuse. We also need to consider the potential societal impacts of widespread quantum computing. For example, if quantum computers can automate many jobs that are currently done by humans, what will happen to those workers? It's crucial that we start thinking about these issues now and develop strategies to ensure that the benefits of quantum computing are shared by everyone.
This has been an incredible deep dive into the world of quantum computing. We've gone from these mysterious qubits to these incredibly precise microwave-wielding traps to the mind-blowing possibilities of this technology. What a journey.
It's been a pleasure sharing these insights with you.
If you're as fascinated by this field as I am, I encourage you to dive deeper into the world of quantum computing. Who knows, maybe you'll be the one to make the next groundbreaking discovery.
The future of quantum computing is bright, and the possibilities are truly limitless.
Until next time, keep exploring, keep learning, and keep diving deep.